As we've seen, variables in Python can be declared and used in pretty minimalistic and straightforward ways. And as in any language, we need a system for scoping, for seeing where those variables are defined and looking up the correct one for our current context inside of a program. Python's system in general for scoping follows rules that'll probably feel relatively familiar to you, though in Python we'll see that there are more contexts that things can belong to, there are more types of scopes, and that the ways that those scopes are allowed to interact might be a little more loosely done than in a lot of languages that you might have seen before. So the sequence in which Python will look at things to try to find a variable if you reference it is local first, meaning inside the current function or inside the current file if you're not working it within a function. So whatever is local to you there. Unless it's explicitly specified that you're going to skip that, like using self dot, or there are some other ways we'll see to sort of bypass the local lookup. Then it looks in any potentially enclosing scope, like if we are inside of a class and then inside of a function within that, then it will look up class variables that might fit within that enclosing scope there. You're also allowed to declare functions inside of other functions. So if you've done that, sort of like inner classes in Java, if you're in some inner function, but you say print x and you didn't declare x in that inner function, Python will look at outer functions. It will look at enclosing scopes like those. Then it looks for things that are globally defined in the module or the file you're working in, or if you're running at the interpreter, then it will look at things that were typed in at the interpreter top level. That's your global scope at that time. And then it will look at built-in things like print and len for length or stuff like that that's built into the language. So this is the general set of rules. Now let's look and see some examples of how those actually work in practice. So as in many languages, functions get a local scope, which includes both local values or local variables and parameters to that function. Those all fall sort of into that local scoping. They also by default get access to global variables. So here I've defined a global variable called glob and a local variable called loc, and both the local and global variables can be accessed inside of my function foo. So in foo, I can print loc, I can print glob, I can print x, the parameter, all of those are fine. Once I'm outside of the function, then the only one of those I have access to is glob. So this is pretty similar to many languages. You define something inside of a local scope, and it sort of stops existing once you're outside of that local scope. And this is generally true. You'll find that it's a little different for things like if statements and loops, that variables defined inside of those still exist after the loop finishes or after the after the if statement has finished its portion of the code. But generally speaking, things that are defined inside of a function or inside of a class, they live inside of that function or that class. But not true the other way around, that global things can be accessed inside of the functions and that sort of thing. Relatively standard. It gets a little tricky, though, when you want to change a global variable's reference. So, as I mentioned, you get access to global variables by default inside of a function or inside of another namespace like a class. And you can even modify them if they are a mutable type. So for instance, lists that are a global variable can be modified. That's no problem. What you cannot do by default is you cannot change the reference that a global variable points to. So here's an example of that. Glob is a string, which is immutable. So it shouldn't be able to be changed in any way as a global variable. And, that's often what we would expect for an immutable thing like that. The list here is a list which is mutable, and so I'm going to be able to modify it globally or within my function. So now let's see how that plays out. We say we want to print glob. It prints immutable global variable. Then we say we want glob to equal, meaning change the reference, right? Change where glob points to in memory. We want it to equal a modified global variable, ? And when we ask to print glob, it looks like we did our job and that glob may have changed. So if you call to foo, then all of foo's statements will act as you would expect. If we look at the ones particular to glob, it first prints the original value, the global value, then it prints the supposedly modified value. But in the global scope, glob is still immutable global variable, its original value. This is not magic. Python doesn't keep track of how you changed glob and reverts it back or anything like that. What happens is this. When you are in a scope like a function and you say glob equals, and glob didn't exist as a local variable there, it creates a local variable. So it does not change the reference of the existing global variable. It just says, oh, you want a thing named glob and you want it to equal this. Great, I'll make you a local variable. And so when you print on the next line, it's that local glob that's getting printed out. When you print it first, you didn't have a local one. So it looks locally, says, no, there's no glob. I'll look globally. Great, here's a global one that works just fine for us. So in many programming languages, of course, this sort of thing would error. Because if I go to define a variable named glob that already exists as a name globally, then my compiler would often tell me, oh, you can't redefine that variable. It already exists. Don't do that. Python will gladly let you shadow that global variable. Shadowing is when you use the same name in multiple scopes. And so once I've said glob equals here, I no longer can access that global version of glob. I can only deal with the local one. So I create a local variable, accidentally perhaps, and then I work with that local variable from then on. But the global one does not get its reference changed. We cannot change where those global variables point to by default. Then the list is mutable. So if I say list.append, appending changes a list. It does not change its reference. It changes the list. So this is no problem. It will gladly change that empty list to have val in it. This acts as expected. It changes the global list and adds val to it. And if I print list, I see the list with val. But on the next line, when I say list equals, that's me attempting to change its reference, which again, as with glob, creates a local variable named list and sets it equal to 1, 2, 3. And from there forward, I'm only dealing with the local version inside of foo. So when I print list, I see 1, 2, 3. And then when I exit foo and I come back out, it is that modified version from the empty list. So this often very much confuses beginning Python programmers. The way that you can deal with this is to guarantee that you won't shadow. So if you think you're going to be using a global variable inside of a function, what you do is you use the global keyword to declare, I would like to be working with the global value or variable named glob. I would like to be working with the global variable named list. And then those changes will be made to the global versions. This says, don't declare me a local one no matter what I do later. Don't do that. Don't declare a local version and shadow it. Instead, when I say glob equals, I want you to be referring to the global version. And so when I say glob equals, that actually changes the reference of the global version and says a modified global variable now within foo and outside of foo. Then when I say that I want to append to list, then it will append it just like before because list is mutable and that works just fine. And then when I say I want list to equal 1, 2, 3, it will gladly change the reference on list to be 1, 2, 3 as well because I said I was using the global one. So this will give you the behavior that you probably wanted in the first place. If you're using those global variables, then you're changing their references as well in here, and that's just fine. There's another option for variables that persist inside of a function, and this is an option that I'm going to have you use in one or more of your assignments as well. And that is you can create static variables for functions using their names to scope them. This is because everything in Python is an object. Functions are objects. That means they get their own variables if you want to use them that way. So this is not a local variable. This is a variable attached to the function's object. So here I've defined a function called countCalls. It does nothing except to count the number of times it's called, and then returns that number of times it's called. So let's walk through some of what it's doing here. It asks, does countCalls have the attribute x? So this tries to look at what is defined for countCalls and says, is that already defined? If it's already defined, then add 1 to it. If it is not defined, then I set it equal to 1 the first time that the function is called. So then at the end, I'm returning the value of countCalls. So if I call countCalls the first time, it's going to see that it does not already have the x attribute, and so it defines the x attribute and will return 1. If I call again, the attribute is already defined, and it will add 1 to it and return 2. If I call again, it returns 3 because the attribute was defined. If I ask to print countCalls.x, that will print out the 3 that was already defined for it. I can, external to the function, change that x value, so do be careful about this, but it's pretty obvious I'm doing it because I'm saying countCalls.x and setting it equal to 0. So then I call countCalls again, and it will set it to 1. Now, it will do so by seeing that it has the attribute x on countCalls and adding 1 to it. And then it will be equal to 1 from there forward until I call countCalls again or until I modify that x value again. So there are other approaches to doing this basic thing, especially the checking whether it's defined. Some people will just try to add 1 to it and then catch an exception, or other approaches like that. These are all okay, but this one explicitly checks, does countCalls have an x attribute already? If not, then we'll create that attribute, and if it does, then we'll just modify that attribute. We wouldn't be able to do plus equals if it didn't already have the x attribute because it wouldn't know what it was adding with, or adding 1 to. When we're doing classes in Python, we can add instance variables or class variables like static variables in other languages. So on the surface, it appears that Python classes have normal instance variables and static variables. We use self or the name of an instance when defining an instance variable, or accessing an instance variable, or changing an instance variable, or whatever we're doing with it. We either use self if we're inside the class, like here, or if we're outside the class, then we use an instance of the class to access it. And if we don't use self or the name of an instance, if we use the name of the class instead, then that refers to static variables. So here inside of my class A, I say CLS equals a class variable. Inside of the constructor, the init function, I say self.inst equals an instance variable. So I've created an instance variable, and I've created a class variable. I state class variable because the class variables are not quite static the way that you would expect them to be in many other languages. And we'll see some examples of that here in a little bit. So I say A equals a new capital A object. I'm creating a new object, little a. If I print little a inst, that will print an instance variable. If I print little a CLS, that will print a class variable. And if I print capital A CLS, that will print a class variable as well. Now, if I change a.cls, then I change it to some other value, and I create a b that is another object of the same type. If I say, is a.cls equal to b.cls, that will be true. And if I print a.inst, it will error because capital A's don't have, this is capital A.inst. Capital A's don't have that instance variables. Only instances of the class have that. Only objects of that class type have that. But class variables in Python can get weird. So I declare the same class I had before, and I declare that little a object. I say a.cls equals a new value. I print a.cls, it will have a new value. Capital A.cls will have a class variable, the original value. So this is again shadowing. It will create an instance variable with the same name as the class variable. So then if I say capital A.cls equals another value, and I print out the two again, I will have a new value for little a and another value for capital A's CLS. Then I create B, that's another object of that same type, that capital A type. I print out B.cls, I get another value, what A.cls had been changed to. Essentially, the way to view this is that used this way, class variables are not static variables. They define a current starting value for new instances, and they can be shadowed if you try to access a variable of that same name, if you try to change the reference of a variable of that same name through an instance, then it's going to create an instance variable of that with that same name. And that will shadow your class variable for that specific instance. It won't change it for everybody. So the best way to use properly static variables is to only reference them using the class's name. We should have only ever done capital A.cls in these. I should not have done little a.cls to change it ever. So similar to our global and local issue, when I try to change the reference, it will just shadow it. It will make an instance variable with the same name, and I won't be able to access it through I won't be able to access the class's version through little a anymore, because if we think back to our scoping rules and how things are looked up, instance variables get looked up before class variables. So it's not good to try to make changes to the static variable or the class variable through an instance. We should have only ever used the capital A .cls to refer to any of these. So I mentioned before that for loops leave their traces behind. Their loop tracking variables and any variables that were declared inside of them can persist in Python. And this can be useful sometimes if we want to know where our for loop quit, for instance, like we were doing a search. We could just quit the for loop, and whatever our I was as we did that search would be the index that we found our thing at. So it can be useful, but it's important to be aware of, because it means that a variable might be defined for a certain value that you didn't remember it having. So we declare I as the loop variable, and we declare v as a variable inside of the for loop. Both of those continue to exist outside of the for loop. And similarly, things that are declared inside an if statement will continue to exist outside the if statement only if the code ever reached the portion where it was defined. So here I have if true, v1 equals will get a value, else, which the else will never happen because my if was based on true, else v2 equals won't get a value. Well, I can print v1 because it got a value up there. I cannot print v2, it doesn't exist. So defining variables inside of if statements can be good or bad for you. Just be aware and make sure that your variable gets a definition in both the if and the else if you're going to use it after the if statement happens. Obviously, don't use if statements that only ever do one portion of them either, but definitely make sure that if a variable needed to be initialized inside the if, that it gets some initialization value inside of the else, or that you check that that variable actually was defined by doing a try-catch or by doing lookups to see what things are defined. How do you do lookups, you ask? Well, you saw the has attribute that can be used on objects and can be used on functions to see if something was defined in their namespace. But you also can do lookups for local or global variables. Dictionaries are very highly relied upon in Python. The lookups for local variables are done using a dictionary. The lookups for global variables are done using a dictionary. The lookups for class variables and functions also done using a dictionary. When I say everything is an object in Python, another argument you could present is that no, actually, everything is a dictionary. So when we do lookups of variables, for instance, that's done using dictionaries. So I can say if v1 is in locals, then I could print out v1, for instance. I know v1 is defined locally, and I could print it out. I can either look it up in locals, or I could just say here plus v1, and I would know that v1 does exist. So this checks whether it's safe to use v1 as a variable name. Same down here, if v1 is in globals, then I know that v1 was defined globally and that I can use v1 without error. I don't know what type of value it has or any of that. We'll get into other things on typing later perhaps. But locals and globals are two functions that return the dictionary that's used to look up local variables, or the dictionary that's used to look up global variables. So again, those would be function locals, not function static variables. We saw those were different. If statement local stuff that's local to your class, etc., and global namespaces for globals. As I said, locals accesses the traditional local variables of a function, not variables that belong to a namespace of an object or a function. Functions are objects. So for those, we can use _dict to look up whether something is in the particular dictionary of that object. So if foo is an object, we can look and see if foo has a variable named v1, has an instance variable named v1. Similarly, if foo is a function, we could do this same thing to say if v1 is a static variable of that function. So all we know is that it was defined in foo's namespace, not what foo is necessarily, whether it's a function or an object or whatever, and we don't know whether v1 is a string or anything else. We simply know it was defined, and we could look it up this way, or we could just say foo.v1 because we know it exists for foo there. There, as I said before when we were talking about function namespaces, there are many different ways to look up whether a variable is defined for that particular namespace, but this is one of them, and this just shows you this principle that variables are looked up in Python using dictionaries. Objects get their own fancy little hidden dictionary. Local variables are a sort of hidden dictionary, and global variables are a hidden dictionary. So we've looked at the rules for scoping in Python, which are pretty standard in terms of the basic principle, looking close like local variables, then looking a little further out at further out scopes, but that how the particularities of Python allow a lot of flexibility. You can just use global variables, and you can just define references for local variables and things like that, but that flexibility might lead to some confusion where, for instance, you accidentally shadow a variable that you were intending to change in a further out scope. That it's more inclined to define a closer scoped version of it, a local version or an instance variable version, without telling you. And so we have to be very careful that we're referring to the specific scope that we intended to, and that we're not shadowing the thing. And that there are some neat creative ways that we can use scopes that may not traditionally be there, like using the namespace of a function to store information across multiple calls to that function.